This is the first of two lessons on differential equations. In this first lesson, we'll look at setting up and solving differential equations, looking at how we find general and particular solutions to them, look generally at the methodology. In the second lesson, we'll go on to solving exponential growth and decay problems. Before we start with the method of solving differential equations, we'll just have a look at a simple differential equation here. A differential equation is an equation with a derivative in it, with any derivative of an unknown function. This particular differential equation tells us that the graph of y has a gradient that's always equal to y. If we have a look at what this looks like on a graph, we've just picked a few examples here. We can have an infinite number of these gradients anywhere on this graph, but by picking several examples here we can see some patterns. If we follow any y equals a constant line, like for example y equals 2, we can see we've got lots of gradients of 2 all the way along the line. The gradient doesn't change. Y is equal to dy dx. Similarly with y equals 4, we can see these steeper gradients, lots of gradients of 4. And as we move down at y equals 0, as expected, we can see all these horizontal lines with no gradient. What the gradient dy dx is 0, y is 0. We can also see all the negative gradients here, like -2 at y equals -2, and the fact that it's the same all the way along the horizontal line. If you look carefully at the graph, you can see that you can follow curves. Like this one, for example, and you can see that the graph curves. There's an infinite number of such curves. We'll have a look at a few. There's some examples of following the curves. By doing so, we create functions that we recognize. We get a family of curves. And what sort of equation do they look like? They look like exponential curves. So, we get a family of solutions, and we call that the general solution of a differential equation. We'll now look at a bit more detail at this function here. The beginning of the solving process involves something called separating the variables. We split the y and the x terms so that they're on different sides of the equation. So we rearrange the equation and we end up with the x terms on the right and the y terms on the left. We can achieve that for this equation by multiplying by dx and dividing by y. So if we do that, the dx's cancel on the left and we get y dx here, and then if we divide by the y's will cancel on this side, so we're left with just dx, and we get dy over y, or 1 over y dy on the left. We're allowed to do that with dy dx. We've done it before. We did it when we did the chain rule. Various other times we've manipulated dy dx like that, because it does behave like that algebraically, even though it isn't actually a fraction. Once we've separated variables, the next step is to integrate both sides, and hopefully you know what the integral of 1 over y with respect to y is. When we're integrating just dx, it's like we're integrating 1 dx, so that integrates to just x. Be a bit careful with this though. We had something like cos dx, then it would just integrate to sine x. So if it was cos x dx, it would integrate to sine x. Don't put random x's in everywhere you see a dx. But if it's just the integral of dx, then it does integrate 2x. So we integrate the left hand side with respect to y, the right hand side with respect to x, and we get this 1 over y, as I hope you remember, integrates to ln y, ln mod of y, because obviously we can only have ln of positive numbers, and then on the right we get x. We need a constant of integration, but we don't need the constant on both sides. We don't need to put plus c and plus c, or plus c and plus d, which would be more appropriate, wouldn't it, as they needn't be the same thing. We just gather them together and put them on the right. So this is our general solution, but at the minute it's what we call an implicit equation. It's not explicitly in the form y equals. So a bit more work to do to make it like that. Well, we know how we can do that. The log's just an index, so if we e both sides, this is log base e, isn't it? Then e ln y becomes y, and we get e to the x plus c. But because of the modulus, we need a plus and a minus sign in front of here. And you can see here we've got our exponential, which kind of proves what we suspected looking at the graph. We can simplify this. E to the x plus c is the same as e to the x times e to the c. E to the c is just a constant, so we can just multiply e to the x by a constant, say k. So we can rewrite this as, instead of this, plus or minus k e to the x, where k is a positive constant. It's more usual to write this as a e to the x, where a is positive or negative. And this is more the model that you see in exponential growth questions. And it's an important result. So dy dx equals y implies that y equals a e to the x. If we go a bit further and now give a value to a, we get a specific equation. So rather than the family of curves, we now have just this one, where a equals 2. And you can see here that, for example, when x is 0, e to the 0 is 1, so y equals a. And if a is 2, we can see that we intersect the y-axis at the point 0, 2. Okay, now it's your turn. Have a go at this question at the top here. Have a go at solving it. Pause the presentation. If you can do this, then that suggests that you've mastered this method and you're ready for the lesson. Okay, so hopefully this is what you got. Step 1, separating variables. 1 over y squared here, cos x dx here. So there we are. Y terms on the left, x terms on the right. Integrate both terms. Well, we've rewritten them here. So that goes up to -1 over -1, cos integrates to sine. So we get y to the -1 over -1 equals sine x plus c. Rewrite that, so it's -1 over y. That looks a bit better, doesn't it? Bring the y down and divide it by -1. We just put the minus sign there. And that's it. If we want to, we could rewrite it as y equals, well, we can cross multiply there, can't we? We would get y equals -1 over sine x plus c. And that's our general solution. If we wanted a particular solution, we would need an x and a y value. So if we knew that x was, say, half pi and y was minus a half, then if we put them into here, you can see that we get minus a half equals 1 over 1 plus c. That implies that c is 1, and then we can just sub back in our 1 into here, and there's the equation.